I'm very grateful to the organizers for having thought it useful for me to give a seminar. But what I'm going to say goes back to many decades, and the only reasonable reason to speak about these things is that they have been forgotten. And the program of analyticity of green functions, let's call them that way, in quantum field theory, this program had raised great hopes at its inception, but after some years of work on it, it proved disappointing. Nevertheless, I think that the algebraico-geometric structure of these things is something which exists and is at the somewhere at the bottom of quantum field theory, and I think it's a structure that deserves some interest. So what I've thought of speaking of is this background structure of generalized retarded functions and the analyticity domain that they provide in momentum space. All right, so at the beginning of this subject, which goes back to the 50s, I think, people wrote some reduction formulae for expressing the reaction amplitudes in quantum field theory. And for example, what I've written at the top here is the formula for the matrix elements of the S matrix in a process which goes from n incoming particles, which are the ones at the right of the formula, and outgoing particles, which are at the left of the formula. And you see, it would be nice if I could. There. Here you see that in the right-hand side of the formula there appears the Fourier transform of something which is called the chronological function, which I'm going to talk about later. And you restrict this function to the mass shell, which is expressed by this way, and the formula contains also something which in local field theory is absent, but for localized fields it's present. It's these intrinsic wave functions. Anyway, that's an example of a reduction formula, and no. People also noted that they could use other reduction formulae, for example, involving, instead of the chronological function, a completely retarded function, which I've denoted R1. And so it was for quite a while, it was not clear why there was these different reduction formulae until people in the 60s began to systematically study the subject of these generalized retarded functions. There were many people working on this subject. One of the principal persons is here in the person of David Ruel. But there were quite a few others, which I won't quote in detail. After some time, a satisfactory picture was obtained. So my framework is, of course, it takes place in Minkowski space, and V plus denotes the future light cone. In Minkowski space, there is a notion of future and past, which is the future of a point is the translated future light cone which issues from this point. And there is another notion which one could say that a subset, for example, subset B is, let's say, later, let's call it this way, later than subset C, if it does not intersect the past of B, the past of C. And these two are equivalent. If a subset is later, B is later than C and C is later than B, then B and C are space-like separated. We assume that we're working in a Hilbert space, although the positivity of the metric plays no role in what I'm going to talk about. So it's also true in the case of, for example, in perturbation theory with an indefinite metric, it's still valid. I forgot to say, we suppose that the spectrum of the energy momentum is, as written in the last line here, the union of point zero, which refers to the vacuum, and a strictly positive mass. The structure of the advanced and retarded functions in position space, in X space, works just as well with zero masses as with non-zero masses, but the properties in momentum space depend crucially on the fact that there are no zero masses. So what I'm going to consider are local fields and localizable. So local fields, they are the familiar local quantum field theory, which commute at space-like separations. But one can also consider localizable fields, which are supposed to be localized in a bounded region, but not at a point. So, for example, among these strictly localizable fields, there are those which occur in the theory of local observables that was introduced by Haag and Araki. And there are also something which is of interest, this this sort of field, which you take several local fields and you convolute them with a test function which is localized somewhere. As you know, there are some states, some particle states, which cannot be created by just one field of a given theory, but require several field theory in several fields, and one has to use something like this. So these objects are localized in a finite region, and this creates some slight differences with a strictly localized field. Now, the main object in this theory is the chronological products. Let's think, for example, of local fields, and we will need the chronological products associated to these fields. I mean, if one could, if the fields were continuous functions instead of distributions, there is a familiar formula for defining a time-ordered product of fields, but in general, fields are distributions, and it's a non-trivial problem to define a chronological product. So for example, the perturbation theory, at least the first chapter of perturbation theory, consists in defining time-ordered product for the Wick powers of the free fields. That it's almost synonymous to at least the ultraviolet problems of perturbation theory is just that, defining chronological products of fields, of Wick products of free field. But we'll assume that it has been possible to define such chronological products, and these things have the following property. First of all, if there is only one field, the chronological product is the field itself. Second property is a property of symmetry, as written here. If you permute the fields which are contained in the time-ordered product, nothing changes. So, and this allows a simplified notion T of x, where x is simply the set of indices that label the field. So here, x would be the set of these indices which are here. The third property is the property of translational invariance. So it's clear what it means. And then the main property is the property of causal factorization. And if the set of variables is partitioned into two pieces, in two disjoint pieces, then if you look at the region where the variables associated with the indices P are later than the variables associated with the variable Q, then you have this factorization. T of x becomes equal to the product of the later fields times the earlier field. And of course, in the case of fields which are not localized at points but at regions, we have to modify slightly the condition and the region where the fields, the later fields are localized must be later than the regions where the other fields are localized. All right, so that's the main property of chronological fields. And associated to that, you have the chronological functions, which are, morally speaking, vacuum expectation values of the chronological products. So if you have a proper sequence of indices, that means a sequence of, a sequence of sets of indices, then what is denoted by this is, morally speaking, this product, the product of chronological products associated to these variables. I say morally because it is also conceivable to define such functions without having had local fields to start with, but by looking at linear sets of these chronological functions. But anyway, we'll assume that our chronological functions are vacuum expectation values of products of T products, like this. And of course, there are distributions in the various variables, and the chronological functions have the following property. Well, they are symmetric with respect to the variables which are contained in one of these packets, x1, x2, and so forth. They are translational invariant, and they have the causal factorization in this sense that if the variables, if the indices labeling the variables are split into two parts, and the variables in the first, labeled by the first part, are later than the variables labeled by the other part, then you have this type of factorization which reflects exactly the property of causal factorization of the T products. And these functions have a property of spectrum, a spectral property, which arises from the spectrum property we've assumed to hold with respect to the translation operator. If we take the Fourier transform of a function of this chronological functions, then its spectrum is obtained in this way. The sum of the momenta labeled by the last set here must be in the V minus, then the sum of the momenta labeled by the other by x nu times x nu minus 1 is in V minus, and so forth. And I'll use this notation Pj. J is a subset of indices, and P sub j is the sum of the momenta associated to these indices. All right. So one can also define truncated chronological functions, and I'm not going to discuss how they are constructed. This is a classical thing, but the support of since the connected time-ordered functions are obtained by systematically subtracting the contribution of the vacuum from the ordinary chronological functions, it follows that the property of spectrum are slightly modified, namely the contribution of the vacuum to the spectrum has disappeared in these functions. Okay. Now one has to discuss an object which a priori has no connection whatsoever with the preceding, and which is a purely geometrical object. You take the n-dimensional real, you take Rn and you call these the coordinates in this S1 to Sn. You define the subset of variables where the sum of all the variables is 0, and now a cell you take in this space. So sigma n is the set of P such that P1 plus of S such that S1 plus Sn equals 0. So that's a hyperplane in Rn. And then you call S sub j the sum a partial sum, any partial sum of these variables S, and it's a sum over a certain subset of the indices, and you denote that by Sj. Now, if you consider the point where Sj equals 0, that's in this space. That's a hyperplane like this. You consider the set of all possible hyperplanes of this type. And the complement of this union of hyperplanes, they are polyhedral cones like this, and they are called cells. They're called n-dimensional cells. So in a given cell, since no partial sum of the S's vanishes, in a given cell, every Sj is either positive or negative. And so you can define this or represent the cell. Let's call this cell S. You can identify it with the list of Sj, Sj1, Sjn, such that they are all positive. The complementary list is the list of subsets that this sign is negative. So a cell is one of these polyhedral cones in which all partial sums of the S's have a well-defined sign. So this is an example in 2 dimensions. In 2 dimensions, we have 3 variables, S1, S2, and S3. We're in the plane where their sum is 0, and you see that there are these various cells which are separated by the hyperplates, as I discussed before. So now, with the help of these cells, one can define the generalized retarded functions and operators. So let's take a cell S with S prime is the opposite cell, and you consider sequences of subsets of indices J1, J2, J nu. They are non-empty, non-intersecting subsets, and you require that, let's say J3, J nu, it requires that the union of every subset, initial subsets like this, should belong to S prime. The union of this belongs to S prime, the union of this belongs to S prime, and so forth, until the last one, J nu minus 1, J nu. You don't require it for J nu, but for J nu minus 1. So that is called a new chain. Now, with the help of this, you write the formulas which are written here. You sum over all these new chains. You sum with a certain sign the product of the T product of the J subsets, and the corresponding vacuum expectation value of this is this quantity. Now,
Henri, can I ask a question?
Yes.
In this formula, J1, the subsets big J1, big J nu, are they time ordered?
No. They are arbitrary subsets of the indices,
Yeah.
with the property that, I mean, they are non-intersecting,
Yeah.
Their union is the whole thing, and they have this property that you consider, I mean, the order is important. So J1 union J2, that should be in S prime. J1 union J2 union J3, that must be in S prime. And so on until J nu minus 1.
Okay.
The Sj that appear in the definition are the sum of the momenta.
No, they are not. They are indices, sets of indices.
But what is the meaning of these real numbers who sum 0?
Yes,
Yeah.
yes.
I'm sorry.
What is the meaning of these real numbers which belong to the coordinates of this?
No. I mean, that's another thing. I mean, the real numbers were designed to define what is S, what is S prime. So S is a list of subsets such that in the cell which you consider, they give positive sums. I mean, I'm sorry for this. it is hard to give a motivation for this, except that it arose in the works of the people which I spoke of before, after quite a complicated elaboration. But that's the result of what they did. So, I mean, it's a definition, you can consider it. Now, so these are the generalized retarded operators and functions. Now, the interesting fact about these expressions is the following. They have support properties in X space. So maybe I'll skip this slide and give the real theorem. The real theorem is that if you take an expression such as the one I have given, it has a support which is the union of certain elementary supports. So as my picture, I hope, shows, you take all possible trees which of the following form. Well, maybe yes, well. The points labeled with a dot are the points such that the S sub j with this particular so you have a cell S, and for example you have in this cell Sj is positive. Then in this tree, J will be labeled with a cross. If Sj is negative, it will be labeled with a dot. And you take all possible trees which have the following properties. Well, the line always connects a cross with a dot. Furthermore, if you cut the tree at a certain line like this, you have subsets of vertices associated with the vertices of this line which I have cut, and the subset which contains the cross should be in S, and the subset which contains the dot should be in S prime. This is the condition for a tree to be associated with this cell. And then, associated with this tree, there is a geometrical support in X space, which is as I've written below. So for each line, you have x sub 2, for example, x sub 2 minus x sub 4 should be in the V plus, and so forth for every line. So this defines a cone in the space of differences of variables in X space. And because we have a tree, these variables are independent. And so they define what one might call a kind of simplicial cone, except that here we have the condition that x2 minus x1 must be in V plus and not positive. It's not a number. It's a vector. So the theorem is that you take all possible trees of this kind associated with the cell S, and then the support of RS is obtained in this way. It is the union of all the supports obtained in this way. Now, if you work out what this if you work out what this means in the dual space of that is in momentum space, well, yes. Yes. Now, if you ask for what the support, you see the function Rs has a support which is contained as a union of things. These elementary supports are not disjoint. They have intersections like this. But a very interesting feature of the support of an RS is that its dual is not empty. Its dual has an interior. And the dual given a cell S, the dual of support of S of support of RS is a certain cone. It's a no. Yes. You start from this RS, and the cone dual to the support of RS, or the corresponding chronological function, is what is written in this formula. So the sum of momenta is 0, and every partial sum of momenta is in V plus if its corresponding subset of indices belong to the list S, and it's in the V minus in the other case. So if you take the Fourier transform of the chronological function as here, then it is the boundary value of a function which is holomorphic in a tube which has this cone as its basis. So that's the tube in which this function is analytic. And you see now that the geometric picture of cells as pieces of as cones in a finite dimensional space is a representation, so to say, or a symbol for the analytic properties of the Fourier transforms of the. I don't know. Is this? I don't know if I've made this clear.
It is quite clear. What is not yet clear, and why do we need so many of these functions?
Because they are there.
But suppose that I'm interested in 2-to-2 scattering. How many functions do I need to consider to be fully happy?
No, you need only one. But it turns out that in momentum space, these various functions coincide in certain open regions. So if you consider a reaction amplitude, so you have certain values for the momenta, they lie in a region. In that region, the chronological function, the Fourier transform of the chronological function, coincide with a whole lot of retarded functions. This is why these people at the beginning of the theory could write a number of dispersion relations. They were the same because in that particular region, these various functions coincided. They did not coincide everywhere. They coincided in this region. But on the other hand, we will now see that I've explained that these Fourier transforms of the retarded functions are boundary values of holomorphic functions in tubes. These tubes, for the moment, are disjoint. But we are going to see immediately that they communicate through certain other regions, and they constitute the branches of a single holomorphic function in momentum space. So, Ruel's identity. So if you take if in the space of these cells, suppose that you have a cell here, S, and a cell T here. They are adjacent along a face, a common face here. Then let's call this plane S sub y. So you have two cells, S and T. Here is S and T. Remember that these are in the space of the real variables S. They are just a model for the domains of these retarded functions. But let's suppose that in this space you have two cells which are adjacent along one of these hyperplanes. S of y equals 0. Let's assume that here S sub y is positive, and here S sub y is negative. And let's say that, so S is a certain list of subsets among which there is Y. And let's call the complement of Y. So S has this set, T has the same sets except it doesn't have Y, but it has Z, because I've crossed this face and gone over to from the place where S is positive, S sub Y is positive, to the place where S sub Y is negative. So S is equal to, no, T is equal to S minus the subset minus Y, but union with Z. Well, in this case, we have this theorem due to Real, and which says that in this case, if we restricted this S to Y, that means we consider the subsets, the list of subsets in here, which are subsets of Y, and we consider the same with the other cells, then one has the following identity, which you obtained. It's with the formula which I wrote for the definition of the retarded operator and functions. It's a simple matter to verify this, that the difference between these two operators, R sub S of X, R sub T of X, is the commutator of the retarded functions corresponding to a smaller number of variables and another retarded operator. Now, this is a very important identity because, well, did I? No, okay. No, okay. All right. So we have this real identity, and now you see on the right-hand side of this identity, the objects which are here could be the same for different pairs of cells. For example, we have here another pair of cells with the same, which are adjacent with respect to the same plane. And it could be that it's not so in the example which I've given here, but it can be that you find on the right-hand side the same expression for different cells. And that's the origin of another important feature of these things, which is the Steinmann identity. So maybe it will be better if I show this picture. Suppose that you have this situation. You have a quartet of cells which are separated by these two hyperplanes, Sy equals 0, Sj equals 0. And you suppose that these hyperplanes, that the intersection of these hyperplanes is not contained in any other one of the hyperplanes which are present in this situation, then you have this Steinmann identity which says that RS plus plus minus RS minus plus, you see, this function minus this function is equal to this function minus this function. So the discontinuity between these two objects does not see this discontinuity here. So these are the Steinmann identities, and they are very important too. Okay. So now let's exploit the real identity to obtain a further property of the Fourier transforms of the retarded functions. So we have the real identity, which I've yes. Here is real identity expressed in momentum space. So you see you have the difference of two of these boundary values of analytic functions, and their difference is the vacuum expectation values of a commutator here. But because of this product structure, this object has a property of spectrum in momentum space, a property of support in momentum space, and it vanishes unless the sum of the momenta in Y is in the spectrum of the energy minus the vacuum. The contribution of the vacuum disappears in this formula. So, as a conclusion, we have this. The difference of these two retarded functions vanish is P belongs to this coincidence region, which is obtained in this way. So, this gives rise. This gives rise to the following fact. One has a theorem in the theory of many complex variables, which is called the edge of the wedge theorem. This edge of the wedge theorem has a long history and has now become very, very refined and so on. But let me give an unrefined version of the edge of the wedge theorem. So, suppose that we have two functions which are locally analytic in two tubes. So, this is a symbolic picture. So, the plane represents the imaginary parts of the variables. Suppose that you have a function which is analytic when the imaginary parts of the variables are contained here, are S, for example, in this case. another function which is analytic in the other tube, RT. These tubes are, in this example, they are disjoint. They are in general position. But now suppose that, I mean, I don't need these tubes to extend to infinity. It's a local property. Suppose that the boundary values of these functions from these tubes coincides in a certain real region. Then these things have a common analytic continuation in an object which is obtained like this. You intersect this with some sphere, depending on this region, and you take the convex closure of this. So you have an analytic continuation of these functions in this region. I mean, this region might be very small, depending on how large the region of coincidence is, but it exists. And so if we consider the various retarded and generalized retarded functions in the momentum space, their boundary values in tubes like this, we've noticed that real identity tells us that adjacent functions like this along a set R coincide in a certain region Ry, and therefore they're tubes which in fact are not very correctly represented by this picture. They communicate in a small open set which is along the real space, along the real variables. And this one will also coincide with this in another small region and so forth. And so we have established some bridges of analyticity between the various tubes of analyticity. Now, so this allows you to define what one calls the primitive domain of analyticity in momentum space. So the primitive domain of analyticity is the union of all the tubes which I described before, plus the little bridges which we have observed, which followed from the edge of the Wedge theorem. And when you consider this, the domain which you obtain in this way, you see that its domain has certain properties, which, in particular, it contains the origin, because all these regions we had these regions of coincidence attached to every subset, Ry, R, Z, and so forth. Z is the same, let's say J. And the intersection of all these Rj's so that's the set of P1, P n in the case of n points, such that, well, of course, momentum space is always understood as the space of the p's such that with a zero sum. That's a consequence of translational invariance. So sigma pj equals 0. This is always understood, but then we have pj squared smaller than mj squared, which is a threshold depending on this index. All these numbers are supposed to be strictly positive, and so the point 0 is certainly contained in this domain. Moreover, if you look at one of these regions, it's in the relevant variable, it's what is in between the two sheets of a hyperboloid like this, and it is star-shaped with respect to this point. So the domain, let's call delta this domain I'm describing. Delta is star-shaped. With respect to 0. So that might seem like a sort of detail, and it is a detail, but it has the consequence, it has the following consequence, that its envelope of holomorphy, you know that if you start from a domain in Cn and you ask for its domain of holomorphy, it's usually not a domain in Cn, it's a Riemann domain. You can just like a Riemann surface has a system of sheets above every point. If you take an arbitrary domain in Cn, it can have sheets too. Its domain of holomorphy could have, for example, let's say, if you suppose that you have a domain like this. No. Suppose you start with a domain which is like this, like a snake which is about to bite its tail. Then you might be able to do a local analytic continuation which covers this part, but you won't get back to the same point. What you get is a point in a covering of this original domain. But in the case of star-shaped domains, you don't get this phenomenon. In the case of star-shaped domain, the envelope of holomorphy is always a Schlicht domain, and it is also star-shaped. So that's for the people who start to try to compute completions of the original domain. It's a reassurance because they don't have to check at every point that they get back the same point as they would have by another method, you always get the same thing. So that's one feature of this domain. Furthermore, this domain is Lorentz invariant because everything was Lorentz invariant in its description. The original domain is Lorentz invariant. Even if we have not assumed that our original fields have Lorentz invariant. Even if the fields are not strictly localized, this is still always true. The domain is strictly in Lorentz invariant. Furthermore, there is an even more interesting property, which is that the envelope of holomorphy of this domain is invariant under the complex Lorentz group. And this is a phenomenon of analytic completion, which is not so hard to prove, and which I would prove if we had more time and more patience, but I won't prove it. Will just state this theorem. The domain is invariant under the complex Lorentz group, not as a consequence of the Lorentz invariance of the theory, but by virtue of geometric properties. Okay. Now, yes, something to remark is the following. You know that if you have, let's say you have a domain like this, say, and suppose that there is a codimension 1, complex codimension 1 manifold, let's say f of z equals 0. F an analytic function, and this is a codimension 1 analytic function, a codimension 1 analytic manifold. Suppose that it does not intersect our original domain. Then it cannot intersect the envelope of holomorphy of this domain. That's an evident property of domains of holomorphy. So, for example, there is one. If you look at one complex vector, this is the tube imaginary. This is This is a domain in Minkowski space, complex Minkowski space, and consider the tube with base v plus. So this domain is the set of points x plus I y, such that y is in v plus. Then, if you take an analytic manifold, which is defined by, let's say, gamma, let's say, which is x plus I, y. This is the Lorentz square. X plus I, y equals A squared. A squared, which is positive or negative. So this this is a hyperboloid in complex space. It never intersects this domain. And in fact, the image of the V plus in the invariance is a plane cut along the positive real axis. So all these points here are outside the image of this in the invariance. So, as a consequence of that, we have certain manifolds which will never intersect which do not intersect our original domain, and therefore will never intersect its envelope of holomorphy. These sets are called cuts. And they are what I've drawn here. And you see, here, this set is the union of over all rho positive of these hyperboloids which I've mentioned before. And here the square must be above the threshold in the canal J. And so this object does not intersect the original tube. It does not intersect the region of coincidence. So it does not intersect the primitive domain. And so these are sort of limits to what one can ever obtain by analytic continuation. Of course, we are far from reaching them. All right. Okay, now I've drawn here the cells in the case of the 4-point functions. This is what we call the Steinmann planet, and the picture must be understood in the following way: we are in the space of 4 variables, S1, S2, S3, S4. We take the subset where this S1 plus S2 plus S3 plus S4 equals 0. That's a 3-dimensional space. So this picture represents something in 3-dimensional space. The cells are cones in this 3-dimensional space, and we can intersect them with a sphere and look on the sphere at the traces of these cones, and that's what we get. So there is a total of 32 of these cells. The names don't matter. I think they're names given by Steinmann originally. I'm not sure. But you see that I might make a point here, which is that this picture is a model for the domain of analyticity of the 4-point function. For example, if we look at this cell, it's a model for a tube, which is defined by saying that imaginary Q3 is in the V plus, imaginary Q1 in the V plus, imaginary Q2 in the V plus. But, for example, if we look at these two cells are adjacent along a common face, as we have remarked before. But the domains in the vectors, domains of analyticity, are not adjacent along a wall. Here we have that Q1 must be in the V plus, and here Q1 must be in the V minus. They do not, their boundary does not have a piece of hyperplane in common. It looks like this. This one has here the tube Q1 in the V plus, Q1 in the V minus. So this picture, which is very useful, is also misleading in this sense. Anyway, that's something one must live with.
And you are saying that the analyticity in SNT is obtained by mapping this on SNT?
Well,
as a consequence?
Yes and no. If I would take the image of a tube, I mean, in the case of the 4-point function, there are traditional notation for the invariants, as you all know. So you have K4 complex vectors, K4, the sum equals 0, and it's traditional to write S equals P1 plus P2 squared not P1, K1. Then we have this relation S plus T plus U equals sigma of zeta J. Now, okay, this is just a notation for the various invariants that one has. It must be also said that the use of the invariants is sometimes very convenient, but sometimes inappropriate, because the map, I mean, you can take as new variables these invariants plus a certain complex Lorentz transformation. You can do that if you like. You can try, and you know that whatever you do, the domains in the complex Lorentz transformation, the whole complex group. So, but the map from the vectors to these invariants is, of course, a holomorphic map, but it has some critical points, and this is very, very inconvenient at times. But in any one is ultimately interested in the mass shell. The mass shell is a complex manifold, in which is given by the fact that kj squared equals mj squared. In fact, we always assume that mj squared, j squared. I should have said that in order to eliminate the single particle poles which are present in the functions, one removes these poles by multiplying by the product of kj squared minus mj squared. The properties of the function which are obtained in this way are the same as before, but except that the thresholds are improved by this method. Anyway,
Henri, now we are getting to the meat of things, and you have many other things to tell us, no?
No, not too many.
Maybe we should plan another talk, as we have...
Well, we can discuss that.
Henri, I think it's important that you get to some intermediate punchline today.
Yes.
But this is all very, very interesting. So since you still have 15 slides prepared, we saw that you still have 15 slides. It's going to be impossible to go through 15 slides, but this is all very interesting. I think it would be nice if you could get to some intermediate punchline.
Well,
and then we organize another seminar.
Maybe
if you can after the new year or something like that.
Well, in any case, just let me state a fact which will show that things are not so simple. This is the mass shell, complex mass shell, and in the real variables it has several connected components which describe the various possible reactions. For example, if we have P3, P4, particles with minus P3, minus P4, going to P1 plus P2, then we must be in a region where P3 is in V minus, P4 is in V minus, P1 is in V plus, P2 is also in V plus. If we were to consider another channel, then we have another region and so forth. So you have, in fact, in the reals you have three regions. I don't know, S, T, U, and corresponding to these three channels. Okay, here is a fact. The complex mass shell does not intersect at all the primitive domain. Does not intersect it. The various submanifolds, which are given by taking one of these conditions, they do intersect the original domain, and therefore they intersect also its envelope of holomorphy. But the the complex mass shell, which is a lower dimensional manifold, does not intersect the primitive domain at all. So every point that you can get, every point of analyticity that you can perhaps obtain on the complex manifold must be obtained by analytic continuation. So, I mean, this is an answer to what you asked. It's true that if you obtain a substantial analytic extension of the primitive domain, then you can map this domain in the variable as these are new other variables, S, T, and U, and some Lorentz transformation. They're other variables. You can map what you get in these variables. Is that okay? I don't know. I don't really have a punchline, but okay. What did I want to say after that? Yes, I mean, I plan to study a little bit what happens in one of these.
But we won't do this quietly with details next time. No?
So maybe we can postpone it to
Let's do
a
this.
hypothetical.
Analytic continuation to the.
And then to another sheet.
Okay, thank you.